Welcome to this e-learning session. We would like to show and demonstrate for you what basic refrigeration is all about. On this screen you see a glass flask with a liquid inside. This liquid is what we call a refrigerant. What is special about refrigerants is that they can exist as liquids and they evaporate at relatively low temperatures. You can see here that the liquid refrigerant is evaporating inside the flask. In other words, the refrigerant is boiling. You can see that bubbles are emerging from the flask wall below the liquid surface and expanding as they move in a vertical direction and at the same time expanding a bit. The outside wall of the flask is here exposed to the ambient air temperature of 21 degrees Celsius we have here. And because the flask in the top is open to the ambient, the pressure inside is the same as the average atmospheric pressure of 1 bar. The refrigerant in this example is named R134A, and it boils at a temperature of minus 26 degrees Celsius in atmospheric pressure. So the temperature inside the flask is minus 26 degrees Celsius. A boiling process needs energy in order to take place because the media, in this case the refrigerant R134A, changes phase from liquid to vapor. We also say that the liquid evaporates. Vapor molecules have more energy than liquid molecules, so energy must be supplied to the media. This energy, in the form of heat, is taken from the surroundings. As long as there is liquid refrigerant in the flask, the boiling will continue, causing a heat transfer flowing to the flask from the surroundings, and in this way lowering ambient temperatures near the flask, so the air temperature in the near vicinity of the flask drops. Other types of refrigerants will have different boiling temperatures, also called evaporation temperatures. Water, for instance, has a boiling temperature of 100 degrees Celsius at the same ambient pressure as we have here. On this slide, you can see a property diagram called saturation pressure for a number of refrigerants. Saturation temperature is just another word for boiling point temperature, the temperature where the liquid starts to boil. For water, this temperature is 100 degrees Celsius at 1 bar, as you surely know. When a single refrigerant is confined in the flask, it will exist in a thermal equilibrium as a mixture of liquid and vapor. The pressure in the vessel is solely depending on the temperature, which is what can be seen on the slide. You can see that the saturation pressure depends on the temperature of the mixture. The higher the temperature, the higher the saturation pressure. The saturation pressure is a unique property of the substance. The different refrigerants do not have the same saturation pressure-temperature dependency. On the slide, you can again see the boiling refrigerant in the flask. The refrigerant evaporates. If the flask is corked or a valve in the outlet of the flask is closed, the vapor produced by the evaporation cannot escape and will therefore stay in the flask. This accumulation of vapor molecules will result in an increase of the pressure. As long as the evaporation continues, the pressure will keep rising. When the pressure in the flask rises, the evaporation temperature will also rise because there is coherence between the pressure and the saturation temperature. which is what the curves show. When the evaporation temperature has reached the ambient temperature surrounding the flask, the heat energy transmission will stop, hence the pressure will stop rising. The end pressure can be found on the y-axis of the curve. When the outlet is opened again, the evaporation process will start up again with increasing intensity as the pressure drops. The flask can represent one of the main components in a refrigeration system. We call it an evaporator. On this slide, you can again see the flask with the boiling refrigerant inside. The refrigerant evaporates, we said. Connected to the flask outlet, we have now added a reciprocating compressor, which is here pumping away the refrigerant vapor produced in the flask. The compressor, as we call it, is the second main component in a refrigeration system. The pressure in the flask still has the same pressure as the average atmospheric pressure of 1 bar, and the evaporation temperature in the flask is also still minus 26 degrees Celsius. In the compressor, the refrigerant vapor is compressed to a pressure much higher than the pressure in the flask. The molecules are pressed closer together. The pressure on the outlet of the compressor could be as high as 8 times the pressure on the inlet. In this example, it is 7 bars. There is coherence between pressure and temperature in the compressor, which leads to a higher temperature on the outlet of the compressor. The temperature on the compressor outlet measures plus 36 degrees Celsius in this case. In order to be able to compress the vapor, the compressor needs a supply of mechanical energy. In this case, an electronic motor is driving the compressor. It is possible to increase the capacity of the compressor. One way of doing that is by increasing the revolutions of the compressor. We are now increasing the revolutions on the compressor, and you can see that the power consumption to the electric motor is also going up. The compressor will momentarily try to pump more refrigerant vapor than produced in the flask, with the consequence that the pressure in the flask is pulled down, causing a lower evaporation temperature. This will again cause a more violent evaporation, as you can see, which will continue because the temperature difference between the ambient temperature and the evaporation temperature in the flask is now higher, giving an increase in heat transmission to the flask. A new equilibrium will be established. It is also possible to decrease the capacity of the compressor below the capacity we started up with. When we reduce the revolutions, the power consumption of the compressor will also go down. The compressor is now unable to pump away the refrigerant vapor produced in the flask, with the consequence that the pressure in the flask will increase immediately, causing a higher evaporation temperature. This will again cause a reduction in evaporation, as you can see, which will stay on this level because the temperature difference between ambient temperature and the evaporation temperature in the flask is now lower, giving a decreased heat transmission to the flask. Again, a new equilibrium is established. You can again see the boiling refrigerant in the flask and the reciprocating compressor pumping away the refrigerant vapor. But now we supply an extra flask and connect it to the outlet of the compressor. This flask is accumulating the vapor from the compressor outlet. In this flask, the refrigerant is cooled down and will start to condensate when it comes into the flask because the refrigerant is exposed to the relatively cold surface of the flask, which is again exposed to the ambient temperature of 21 degrees Celsius on the outside of the flask. On the inside walls of this flask, you can see that liquid drops are formed and running down the walls to the surface of the liquid in the lower part of the flask. A condensation process needs to give away energy in order to take place because the media, in this case the refrigerant R134A, changes phase from vapor to liquid. The vapor condensates. Liquid molecules have less energy than vapor molecules, so energy is subtracted from the media. This energy, in the form of heat, is given away to the surroundings. As long as vapor refrigerant is supplied to the flask, the condensation continues, causing a heat transfer flow from the flask to the surroundings. This process is exactly the opposite as what is going on in the flask on the left side of the picture. The flask on the right side of the sketch is representing the third main component in a refrigeration system and is called a condenser. Here you see a fourth main component added to the drawing. This expansion device closes the refrigeration circuit and secures that the condensed refrigerant in the condenser flask is returned to the evaporator flask, preventing it from running dry. The expansion device could just be a narrow hole. We call it a nozzle here. In our demonstration, the pressure is reduced from 7 bars to 1 bar in the expansion device, which we can follow on the pressure gauges. Moreover, the temperatures are reduced from approximately plus 27 degrees Celsius to minus 26 degrees Celsius, which we can also follow on the thermometers. As you can see, we measured plus 27 degrees Celsius and 7 bars on the inlet to the nozzle and minus 26 degrees Celsius and 1 bar on the outlet of the nozzle. Furthermore, the liquid will change phase in the expansion device during the pressure reduction, but only partly. This means that the refrigerant will become partly liquid and partly vapor when it leaves the nozzle and enters the evaporator flask. If you listen closely, you can hear that this expansion process produces a slow hissing sound. It is actually possible to divide the refrigeration plant into a low pressure, low temperature part and a high pressure, high temperature part. We can visualize this by drawing a dotted horizontal line through the compressor and expansion device. On the left, we have the low pressure, low temperature side, and on the right, we have the high pressure, high temperature side. We can also make analogies over the four main components as demonstrated here. The analogy for an evaporator is a kettle which boils water. The evaporator is doing exactly the same, but instead of water, it uses a refrigerant that boils at very low temperatures. The analogy for a compressor is a bicycle pump, which compresses the air and pumps it into the tire. The compressor is doing exactly the same, but with a refrigerant instead. The analogy for a condenser is a cold window or a cold glass of beer, where the water vapor in the air condenses on the surface. The condenser is doing exactly the same, but it is using refrigerant that condenses at high temperatures and pressures. The analogy for an expansion device is an aerosol can that expands the propellant through the nozzle when you squeeze it. The expansion device in a refrigeration plant is doing exactly the same. We can show you a dynamic demonstration of how a refrigeration system works and how it is utilized. For example, for storage of food. We are here building a small cold room around the evaporator flask. The cold room has walls that are well isolated from the space outside the room, where we still have a temperature of 21 degrees Celsius. The pressure in the evaporator is still the same as the average atmospheric pressure of approximately 1 bar, with a cohering temperature of minus 26 degrees Celsius. Now that the cold room is isolated from the outside, it is possible to pull down the air temperature in the cold room because the heating energy is taken for the evaporation. This room temperature will stabilize when the heat transmission through the isolated wall is the same as the heat transmission through the flask wall. In this example, the room temperature stabilizes at minus 16 degrees Celsius. Now that we are increasing the revolutions of the compressor, the power consumption to the electric motor driving the compressor is also increasing. The compressor will now circulate more refrigerant in the system, as you can see. The consequence is that the pressure and evaporation temperature in the evaporator flask will go down, and the evaporation process gets more violent. The higher temperature difference between the refrigerant in the flask and the room temperature will result in an increase of the heat transmission, which will subsequently cause the room temperature to drop. A drop in room temperature will also result in an increased temperature difference between the room temperature and the ambient temperature outside the room, causing an increase of the heat transmission through the room wall. A new equilibrium will now emerge when the two heat transmission flows equalize. The result is a lower room temperature. In this example, the temperature is reduced from minus 16 degrees Celsius to minus 20 degrees Celsius. When the compressor delivers more refrigerant to the condenser flask, the consequence is also that the pressure and temperature in the condenser flask goes up, and the condensation process gets more violent. Now that the temperature in the flask is higher, the heat transmission to the ambient will increase because of the higher temperature difference. A new equilibrium will occur when the heat transmission energy streaming from the flask wall to the ambient is the same as the energy changing phase from vapor to liquid.